Now we're going to introduce the Green's theorem. Suppose C is a positively oriented, piecewise, smooth, simple closed curve. Positively oriented. Piecewise, smooth, simple closed curve. In the plane, okay. And suppose D is a region bounded by curve C. And let D be the region bounded by curve C. Suppose you have P and Q that have continuous partial derivatives. Let P and Q have continuous partial derivatives on an open region that contains D. Open region that contains D. Then the line integral of P dx plus Q dy over C can be converted into double integral over region D, partial derivative of Q with respect to X, minus partial derivative of P with respect to Y, dA. This is Green's theorem. You can convert a line integral into a double integral under the following conditions. For example, suppose you have the following example. The question says, evaluate example. Evaluate the integral of 3y minus e to power sine x dx plus we have 7x plus square root of y to the fourth plus 1 dy over regions over curve C, where C is the circle, where C is the circle, x squared plus y squared equals to 9. Very good. I have my P of X, I have my Q. Q of X and Y, Q of X and Y. All right. So if you take partial derivatives of either of these, those partial derivatives are continuous. The same here. Very good. So you have a line integral and you want to convert your line integral into double integral over region D. Is it going to be the disk inside the circle and on the boundaries? So let us apply the Green's theorem. P of X and Y is equal to 3y minus e to power sine x. So I need to find the partial derivative of P with respect to Y, which is just 3. The Q of X and Y is equal to 7x plus square root of y to the fourth plus 1. And I need to find a partial derivative of Q with respect to X. Partial derivative of Q with respect to X, which is equal to 7. So this integral becomes the double integral of partial derivative of q with respect to x, 7, minus partial derivative of p with respect to y, 3 dA over d. So take a look at this. I just converted this ugly looking line integral into a double integral that is very easy to work with. This guy is equal to double integral of 4 dA. You can say that, hey, since I have a circular region, I can convert everything into polar form. So this guy becomes integral 0 to 2 pi integral 0 to 3 4r dr d theta. Fubini's theorem says, hey, you can separate these. I have 4 integral 0 to 2 pi d theta times integral 0 to 3 r dr, which becomes 4 times 2 pi times a half r squared, or 9. Can cancel out 2 and 2, 36 pi.